Hello everyone, my name is Dr. Vile and welcome to my A-Level Chemistry YouTube channel. This channel is all about getting you ready for your A-Level Chemistry exams. Please make sure to like, subscribe to the video and share with your friends if you found it helpful. This particular video is going to be looking at ionic bonding. So we're going to look at how to draw ionic bonding diagrams and we're going to look at some of the physical properties of ionic compounds. So when you have an ionic compound, it's always formed between a metal and a non-metal. So I've got an example here of sodium chloride, where sodium is your metal and the chloride comes from chlorine. Notice the N changes to a D once it's bonded, which is your non-metal. So one of the things that you'll be asked to do on your exams is to draw the bonding diagram for this. So the simplest way to do it is to start off with the atoms and work out how many outer shell electrons they have. So I'm going to just focus on the outer shell here. Now sodium is in group 1 and it'll have one outer shell electron. So I'm going to draw sodium, I'm going to have a circle around it like that, and I'm going to put a cross to represent the one outer shell electron. And then chloride, which comes from chlorine, has 7 outer shell electrons because it's in group 7. So I'll draw the circle there and I'm going to draw 7 dots to show the 7 outer shell electrons. Now at this point, the sodium has 1 electron too many, one in its outer shell, and it will be far more stable if it can get rid of it. And chlorine wants 1 electron to have a full outer shell. So we show an arrow going from the sodium to the chlorine to show the electron transfer across. Now at this point, you need to draw the ions that form. Well, sodium has lost its outer shell electron, so its new outer shell has 8 electrons in it. And what we do is we show those 8 electrons. Sometimes it's okay to leave it completely empty to show that the outer shell is empty. Put that in square brackets. And we put a positive charge to show that the sodium has lost 1 electron. And then we go to the chlorine, draw the circle again. You've got the 7 that were there already. And then we've gained 1 electron from the sodium. Now notice I've drawn a cross for that to show that it's come from the sodium. Put that in square brackets. And it's gained a negative charge because we've gained 1 electron. So when you have sodium chloride, you've got Na plus and Cl minus, and the charges balance, 1 plus and 1 minus. So the formula for sodium chloride will be NaCl. Okay, let's take a slightly more complicated example, magnesium fluoride. Now magnesium has 2 outer shell electrons and fluoride, which comes from fluorine, has got 7 outer shell electrons. So start off with the magnesium. And we'll draw those using crosses. It doesn't matter which way round you do the dots and crosses as long as you're consistent with your style. And then we'll draw one of our fluorines with its 7 outer shell electrons. 1, 2, 3, 4, 5, 6, 7. So the magnesium donates 1 of its electrons to the fluorine, but you can see that the magnesium still has 1 outer shell electron, so we need a second fluorine with 7 electrons. And we transfer the second electron from the magnesium to the fluorine like that. Now what this creates is our ions. Let's start with the magnesium. The magnesium has lost its 2 outer shell electrons, so it now has its next shell, which has 8. So 2, 4, 6, 8, or you can leave it with 0. Check your mark schemes on that to see what they show, but either should be fine. That now has a 2 plus charge because it has lost 2 electrons. And then go to the fluorine, draw the circle. The fluorine had the 7 dots to start with. But you can see that it's gained 1 electron from the magnesium like that. Now each of these has a 1 minus charge, so we put minus up at the top, but there are 2 of them. So down at the bottom left, I'm going to put 2 times. Don't get this confused. It's definitely a 1 minus charge, but there's 2 of them. Okay. Some people put 2 minus there, and that would be wrong. It's 2 lots of 1 minus. Before I move on from that one, sorry, I should have said that the magnesium is Mg2 plus, and the fluorine, which becomes fluoride, is F minus. So have a look at these charges here. You've got a 2 plus for the magnesium and a 1 minus for the fluorine. You need 2 lots of the F minus, and therefore the formulae becomes MgF2. That's really important. Let's clear that, and then I'll move on to the next example. This example is sodium oxide. So sodium has got 1 outer shell electron. It's in group 1. And oxygen has got 6 outer shell electrons, which will show as dots. So we have an electron transfer from the sodium to the oxygen. That gives it 7 electrons, which isn't enough. We need 1 more. So here's a second sodium, which transfers its electron as well. Now what that leaves us with is the sodium ion, which now has either 0 outer electrons or 8, depending on perspective. I'll draw it with 8. And that has a 1 plus charge, but there are 2 of them. And then the oxygen, which had its 6, 1, 2, 3, 4, 5, 6 in dots. But then it's gained 2 electrons from the sodium. So it has a 2 minus charge. In terms of the formulae, it would be Na2O. By convention, the metal always goes first. So Na2O. Finally then, a comment about the physical properties of ionic compounds. It's probably a good idea to actually define what we mean by the ionic bond at the moment. You've created these ions by either gaining or losing electrons. So the ionic bond, as you can kind of see in the diagram there, is the electrostatic attraction between the oppositely charged ions. Positive and negative attract each other. In sodium chloride, they arrange themselves in this cubic structure, which maximizes the attractive forces while minimizing the repulsive forces. So it's opposite reds and whites, which are the chloride and the sodium ion. In terms of physical properties, firstly, they've got high melting and boiling points. The reason is the ionic bond is very strong. You have a strong electrostatic attraction between the ions. So it takes a lot of energy to overcome this strong electrostatic force. But the melting point and the boiling point depends on the charges. So have a look at the example I've just put there. Sodium chloride has Na plus and Cl minus. So notice it's 1 plus and 1 minus, whereas magnesium oxide has Mg2 plus and O2 minus, so 2 plus and 2 minus. The bigger the charge on the ions, the higher the melting point. So magnesium oxide has a much higher melting and boiling point than sodium chloride. That's due to the size of the ions. The charge density matters as well, so the actual size of the ion, that makes a big difference. The greater the charge density, the higher the melting point as well. Ionic compounds are generally soluble in water. I've used the word generally there because not all of them are. I'm not going to go into the thermodynamics of that in this video, but they are generally soluble in water. Now, they do not conduct electricity as a solid. The reason is, if you look at this diagram here, the ions are held rigidly in place and cannot move as a solid, and the ions need to be able to move to carry an electrical current. However, if you melt your ionic compound or dissolve it in water, the ions are free to move, and then the ionic compound becomes a conductor of electricity. So the ions need to be mobile. Well, I hope that was a quick whirlwind tour of ionic bonding. I've started to make videos again, so do keep checking back. I'm going to be working through a bit on covalent bonding and then some on intermolecular forces soon. So keep checking back over the next week or two. Thank you for watching. Please make sure to like, subscribe, and share with your friends. Take care, everyone. See you on the next video.